So in this video we're going to go over the idea of a subspace, and then we're going to identify what we need to demonstrate to show that a subset is a subspace. So a subspace is a pretty simple idea. The idea is if you have a vector space Rn and then you take a subset of it, if that subset that you take has all of these properties of vector addition and scalar multiplication, if all of these things are true, then the subset is a subspace. In other words, it forms a vector space in its own right, even though it's only a subset of Rn. As long as it has all of these properties, then we call it a subspace. And the nice thing is to show that something is a subspace, we actually don't need to go through and prove that each of these properties hold for the subset. We only need to show two things, and this gets back to the earlier conversation about closure. So if we can show that the subset is closed under vector addition and scalar multiplication, that's sufficient to ensure that the subset has all 8 of the properties that are listed here. So remember, closure under vector addition just means that if you've got a set and it has, say, a vector u and v in it, that the closure under vector addition guarantees that in the subset u plus v lives in there also. And closure under scalar multiplication would just say, hey, if you pick any scalar c and multiply c times the vector u, if u is in the set, then we're guaranteed cu is in the subset and cv is in the subset. So that's what closure means. Hey, when I take two things from the subset that I'm working with, the sum of those two things is also in the subset, and any scalar multiple of something in the set is also in the subset. So the first thing is to identify why closure of under vector addition and scalar multiplication is sufficient to demonstrate that a subset has all of the properties. So let's just look at this first one, the commutative property of vector addition. Let's just think about this for a second. The idea is that if you take a subset, the subset is going to inherit the commutative property. I think I said the wrong property on accident. The subset is going to inherit the commutative property from the superset, from Rn. Here's what I mean by that. Let's suppose we were just thinking about real numbers. So all real numbers, take a subset of the real numbers. So a subset of the real numbers could be 2, 3, and 5. There's a subset of the real numbers. We know that for real numbers, we know that if we have real numbers a and b, that a plus b equals b plus a. And so the idea is if I take a subset of the real numbers, 2, 3, and 5, 2, 3, and 5 should inherit this commutative property from the superset, which is all of the real numbers. So 2 plus 3 should equal 3 plus 2, for example. And we know this has to be true because if you could demonstrate that two elements in the subset didn't commute, you would have proven that the superset, the original set, didn't commute because you would have a counter example. So the idea is that most of these properties get inherited by the subset from the superset. The commutative property gets inherited, the associative property gets inherited, the distributive properties get inherited. Multiplication, the existence of the multiplicative identity, the scalar 1 times u, these are things that are going to be inherited. Maybe not. Maybe this one needs a little bit of justification. But here's the idea. Here's the idea why closure under addition and scalar multiplication is sufficient. So if you're closed under scalar multiplication, that means that if you have a vector u, any c times u is also a member of the subset. So here you've got negative u, the existence of an additive inverse. Well, negative u is just negative 1 times u. So if your set your subset is closed under scalar multiplication, then you're guaranteed that negative 1 times u, which is negative u, is also in that set. So closure says, hey, no problem, negative u is in there. And the moment you know negative u is in there, you know that additive inverses exist. Every element in the subset has an additive inverse in the set if you have closure under scalar multiplication. And you could use that same line of reasoning to justify this. If you're closed under scalar multiplication, then 1 times u is going to be in the set. Although I don't really need to justify that, I suppose. So the closure under vector addition then is important, because if you know u is in the set and negative u is in the set because of closure under scalar multiplication, then if you're closed under vector addition, then u plus negative u must be in the set, which guarantees that the 0 vector is in the set. And one of the properties that you have to meet is that the 0 vector must exist for you to have a vector space. So that's kind of the rough justification. If you're closed under scalar multiplication, that guarantees that you have inverses. If you're closed under addition, then you're guaranteed that you have the 0 vector. The other properties just get inherited from the superset.